Good afternoon, it's Tony Peters. I want to try to make this update as quick as possible. Been plugging away all through the night. It's about Friday afternoon at 1 o'clock, and I want to cover a few things with you on an update on the beta angle position and control system, as well as the proximity warning system. But I also wanted to take this opportunity on a video to quickly go through the questions that you had, Dr. Salafar. Forgive me for not responding to you last night. So I'll just get right into it. So the maximum power point tracker built into the NEMA 17 controls in order to capture the maximum energy as the PV cell rotates. Well, in my test setup, the PV cell is not rotating. It's actually staying completely static on the ground or on the thermal base plate, or it's mounted to a structure. So what I have here is a 1/20th scale cutout cross-section of a Triton UAS that I got courtesy of Professor Ames last time I was out there. And what I wanted to do with this setup was, okay, so instead of just using a flat solar cell, which you can evaluate any kind of solar cell you want, plug it in and then see what kind of values you get. But for argument's sake, what I want to talk about, address your question, is the, let me move this chair out of the way, the PowerPoint tracking, which would be, I'm assuming, synonymous with hey, are you using single or dual axis tracking? I know we kind of talked about it before last time I was out there, but the cell is going to be static along an airfoil wing. And if you try to use, if the sun's behind you, this is the leading edge, this is the trailing edge. If you try to move it, if the sun goes behind you, you're going to create a lot of drag, and it could damage the solar cell equipment. It could actually pull it right off depending on the speed you're going. And then if you put it this way, if you put it this way, what will happen is the sun's coming at it and it's trying to get that. It's actually going to spoil the airflow over the over the trailing edge of the airfoil, and it's going to reduce the amount of lift that you have. And in order to compensate for that, your airfoil is going to have to do this, and your solar cell is going to have to move even more and more up, which is going to defeat the purpose, I think. And then for lateral or Z-axis or roll axis type configurations, you're going to be doing a lot of this, and it could throw off, again, it's going to have to be raised in order to actually do anything, or recessed, and that could impact the coefficient of lift as well. So what I'm planning on doing is keeping the solar cell static and moving this assembly, the artificial sun module subsystem, over top of a solar cell to get an idea of what the solar day profile would look like. And it's usually a bell curve. I have an example in my PowerPoint presentation where I'm using a LabVIEW calculator, and what I'm going to do is take, so from 0 degrees, so sunrise to sunset, it says that you got a certain amount of power in terms of IV, and it's going to be measured. So to answer the second part of your question, so of the first question, it kind of sounds like, how am I going to capture that maximum energy? Well, in this configuration, the maximum energy is going to be straight 90 degrees when the angle of incidence is normal to the cell. And this whole setup right here is my photocurrent measurement subsystem. And I realize I haven't talked a lot about that yet, but I've been doing a lot of work on it, trying to get not to get sidetracked with additional experiments that I want to run with it. But I have my SD card module on top of my controller here. And what I'm going to do is I have a real-time clock that I have to install on that setup for my current sensor. But I got a couple different things on that. I'm going to work on that a little bit later, but because my priority is the beta anchor control system and the environmental control system, and then probably fabricating everything to the point where it's moved out of the experimental phase into the prototype phase, where I'm not just using breadboards everywhere. So what that's going to do is actually input all of my IV data, my time, my date, my angle that I'm using, all over the course of the cell, and then I could just put it right on an SD card, throw it in Excel, and output any kind of data I want, or manipulate the data any kind of way I want or need to. So I'm looking for that characteristic bell curve, and I can integrate the area under the curve and get the total solar power you can anticipate for that day. And then, of course, I can make adjustments based off of winter and summer solstice, geographic location, and I could do all those ex post facto calculations. So moving on, I think if I didn't answer your question directly enough, we'll probably have a telecom we'll link up. Second question was with the cost of the PV cell in the box. The smaller one that I had shown, it was very, very thin. That's the triple junction gallium arsenide cell, and it runs about $350-ish. So that's, you know, what kind of leads into the third question for why a proximity sensor? Why would I care? Why would anybody care? So I have two different ways of doing this. One is using the ultrasonic sensor setup that I have here. What I'll do is I'll take my camera and I'll kind of show you what I did here. I put this all together and wired it up at the edge of my array, or not my array, at the edge of my mechanical arm for my BAPCS. That entire area right here is where the artificial sun module subsystem is going to go. And initially I thought to myself, well, I'll use an ultrasonic sensor because it'd be great, but started running some issues, and I thought, okay, well, I can use it as a proximity sensor because I have ton of flight sensors that I can use for LiDAR, for light detection and ranging, which would be great because I want to know what the distance is between the source and the solar cell. So I'm trying to make everything as contactless as possible. So this way I can just get the real-time distance as it's hitting it from different angles. So that'll help out with my calculations, at least get an idea. So if I move it farther away, I get a certain amount of lux, I get IV from that. Move it closer, I get a certain amount of lux from there, I get a certain IV, and then I can start to see what my data looks like and my trends and how they change. And then I can run some analysis of variance on those and look for statistical significance. So the proximity warning system, you got a lot of fragile stuff, a lot of expensive equipment. Sometimes it's not just going to be this. Somebody might come into the lab and say, hey, I want to test this thing out, but it's got this whole thing behind it. Let me put that in there. You want to be able to know without having to do a whole bunch of rehashing of calculations and looking at it through the box, or if you even can. I haven't thought about that far ahead, but I think it's good to have two things. One, an idea of, or actually a few things. One, an idea of how far this is away from that to start with. Two, the shape of the structure that you're working with. Three, the ultrasonic sensor actually working on both sides in tandem, and it calculates either side. It's just going to tell you, hey, something's getting too close. Within 50 millimeters, buzzer goes off, red lights go off, and it'll actuate a kill switch. The fourth thing that I'm doing to as a safety measure, because these things come up, the proximity warning system, it wasn't something I planned on doing, but it was something I thought there might be a perceived need for because of the nature of the sensitive equipment or the test equipment, excuse me, the test cells, would be kill switches, and actually only having my NEMA 17 able to go from 0 to 800 steps. And I'll talk about that here in a second after I'm done answering the fourth question, which was the Raspberry Pi. So availability of the product, cost of the product. I know a lot of people who use Raspberry Pis, they swear by them. Some people swear by Arduino, the Italian company. Some people swear by the Metro boards. There's so many different ones out there. I remember as an undergrad, I had to build the microcontroller from scratch because there weren't a lot of these things and they were very expensive. So now it's great because they come in different sizes, they come in different model types, the minis, the medium-sized boards, the large ones. You can stack them up. Personally, I like both boards. Raspberry Pi was just a little bit more expensive at the time when I was putting all this together. All the extra components that I needed, I was able to get kind of like a bulk price on some of my Arduino and Metro kits from DigiKey Electronics. Some of the Raspberry Pi boards were sold out that I wanted, but I have tons of different boards to try out. But really what it boils down to is cost, schedule, performance. Performance was near identical. The cost was a little bit more. And in terms of schedule, the availability of the Metro and Arduino versus the Raspberry Pi. I know I could buy some of those on Amazon, but it was just something that I decided to stick with. There's still C++ based programming language, but there's just personal preference. So without wasting any more time though, hopefully I answered your questions. If I didn't, let's try to link up and have a telecon. Like I said, I was trying to keep this video short, but I'm already at 10 minutes. So what I'll do is I'll put when I send the link out for this video, I'll say just skip to like 10 minutes and 30 seconds if you want to see the demo of what I have going on so far. So the beta angle position control system is a priority because I need very precise angle measurements and feedback for me so that when I do my calculations, I know exactly where the source is coming from. What is the angle of incidence on that cell at any given time, where I'm trying to correlate that with characteristic performance. I'm getting this much current under this frequency or this wavelength of light, but what angle is it coming in at? That's what's going to help me build that characteristic bell curve. So what I've got right now is I've got my new driver, my Metros hooked up. This is the first time I've actually hooked up two different subsystems at the same time. So kind of a leap in the positive direction here, making positive displacement towards my end goal. I thought of a couple other things. One was a laser measurement tool, or at least just a 5 milliwatt laser, so you can get an idea of where you want to have your board set up in relation. So I want to have it going over the bypass diode, or I want to have it just directly centered over the cell. No big deal. You can leave it on, but it's just something that I'm using for calibration, and so you have an idea without trying to eyeball it. You could be precise. The LED ring will be centered around that laser, so you'll know that everything's centered up the way you want it to. Right here, my proximity warning system, which I'm sure you've heard go off. You know, it's gonna have a red light go off as well as the piezo. It's pretty loud. I have it set that way to be pretty loud. So real quick about the NEMA 17. I had some issues with torque. I was able to increase the amount of amps going to the system through the driver. It's actually got a potentiometer. Lesson, use a ceramic screwdriver, which I was able to get. Very, very, very tiny one. Do not use a regular screwdriver that's grounded, even though I have an electronics screwdriver set, a precision screwdriver set. I suspect that it didn't work out very well. So 200 steps per 360 degree rotation. That's a great place to start because I'm using my serial monitor in my code or in my program here to actually control the amount of steps that it's going to take, and it correlates to an angle. And I'm like, here I can figure this out. So some basic math, and I can have it programmed in. So right now everything's controlled through the computer, but I'll demo it. So 360 degrees for 200 steps, it's 1.8 degrees per step, as advertised. That's in full step mode. The micro step feature enables me to take 1/8 steps. So henceforth, if I have 180 degrees, which is what the code is limited to, like I talked about as like a safety aid, because it won't go past that. It won't let me put in 1,000 steps and go all the way over. But 180 degrees is 100 steps. So in microstep mode, 180 degrees is now 800 steps. So 100 times 8. So if I do the division there, it's 0.225 degrees per step. So what I'm going to try to do is set a keypad, and the keypad is going to be good. I think I'm going to get rid of the rotary encoder because I'm getting a lot of negative feedbacks in my loop, because it could be skipping steps, it could be, it's just not catching up. I can go into that later as to why I'm thinking about scrapping it, but I got the idea from my old robotics class where you're working with a CNC and you had a 4x4 keypad and you put in an angle, you put in a step, or you put in something and enter, and it manipulates the entire arm to where you want it to go. So I thought that would be a really good idea. So my command line would just say, I want to move this amount of degrees. So it would interpret that as, the code says, translate that steps times 0.225 degrees. So with that being said, I was able to measure this and work with it all night. And originally I had plus or minus 0.5 degree margin error, plus or minus working that. Now it's about plus or minus 0.15 degrees. So I can program it in very, very, very accurately, and it'll actually move to where I want it to go. So I have a homing function. I use this switch right here, and what it does is it'll, very low torque, very low acceleration, it'll steadily move, hit the switch, and then bounce back off. Once that's done, it says that's your new 0 position, and then it goes to 800. That's your full range of motion. So I'll demonstrate for 0 degrees, 45, 90, 135, and 180 degrees by 0 steps, 200 steps, 400, and 600, and 800 steps. So take it through the full range of motion. So just to demonstrate though, I will turn the laser back on, so you can kind of think about that as that's where the artificial sun module is shining either red, green, or blue at any given point in time, and it runs through its full range of motion. So I'll actually just hit the reset here, and it'll show you the homing function. And it'll actually go there. It thought that it was going to hit something, but it bounces back. That's what the code is supposed to tell it to do. So let's go to 45 degrees, 90 degrees, 135 degrees. And then this one, I think the buzzer will go off, but there you go. So what we'll do is we'll bring it right back up to 90 degrees. There you go. Back and centered, right back on where you want it to be. Like I said, a couple different things going on right now. Next steps, I'll probably send out an email with my future plans and what I'm going to try to do from there. But right now, this is pretty monumental for me. Just trying to get this whole thing set up. I'm going to work the interface and everything else over the weekend. I've put some more part requests in. Hopefully I get those sooner rather than later. And as always, any questions, feel free to ask. And if I didn't answer your questions, or even if I did, hopefully we can have a telecon here shortly and discuss some of the progress and path forward. Thank you for your time.